Alright, so this video is going to be an explanation on the chemical shifts of protons on sp2 and sp hybridized carbons. So, for example, if we have an alkene and a benzene ring and an alkyne. Let's just say we have that, and then we want to see more or less where these protons are supposed to show up. Now, we've already mentioned this before. For alkenes, they show up around 4.5 to 6 ppm. And then for benzene rings, they show up around 6 to 8 ppm, or maybe 6.5 to 8. And then alkynes are going to show up at around 2.5 ppm. Okay, so based off of kind of the idea of electron density and shielding and things like that on the protons, these are kind of in weird areas on the NMR spectrum. And so we definitely need to kind of explain that further. And so let's talk about these guys first. So the sp2 hybridized carbons. Now, let's specifically go over benzene first. So the thing about electrons is that they are always moving and they're not stagnant. And so since they are charged particles, they do create their own magnetic field. And so when we have pi electrons, like, let's scroll down a little bit more. Let's say we have pi electrons like on benzene. And then these pi electrons, as you know, like at least for like resonance purposes, they're kind of loosely held electrons, and so they move around, and they can actually move around to the point where we have almost like just like a circle like that, and that's kind of why we draw resonance structures like in this manner. Benzene rings can be abbreviated with this 6-membered ring with the circle in the middle to indicate that this is like an never-ending cycle, right, of the shifting of pi electrons. And so these circulating pi electrons, they create a ring current. Okay, so what I want to do is try my best to draw this for you. But again, when we are in an induced magnetic field, we have B naught. That's our induced magnetic field. I'm sorry, that's the applied magnetic field. And if we have a benzene ring, let's draw this guy. So I'm going to draw this a little bit, almost like a wedge, just to indicate that we're kind of angled. We took the ring and we tilted it backwards a little bit. And so we're looking at it at a slight angle. And if we are looking at the flow of these electrons, okay, so with the electrons circulating around that ring in a counterclockwise motion, that creates an induced magnetic field, and that induced magnetic field is essentially circulating through the ring and outside on the and then also on the outside, and we're going to create an induced magnetic field that looks like this with, let me change the setting for this guy, where the arrow or the direction of that induced magnetic field is going in. On the right side, it's in a counterclockwise motion, and then on the left side, it's in a clockwise motion. Sorry. Okay, so that way they're both kind of heading more or less in the same direction when they come down this center, right? Now, what we want to focus on or point out is that if we have a hydrogen kind of sticking out here or sticking out here, that hydrogen is experiencing that induced magnetic field. It's basically the way I've drawn it. They're like all up in that induced magnetic field, right? And so they are feeling more or less and like almost like a new applied magnetic field, or the induced magnetic field is amplifying the applied magnetic field because the induced magnetic field is actually heading in the same direction as the applied magnetic field. Okay, so these guys are the induced magnetic field. And it more or less amplifies the applied, or I don't want to say amplifies, I'm sorry, I think it basically it just reinforces the external field. Okay, and so what does that do? Essentially what that does is, remember when we're talking about the applied magnetic field and how much that proton feels based off of the electron density, since this proton on the ring and that proton on the ring, they feel a greater magnetic field, they are de-shielded. Okay, and so what that does is it shifts them to larger ppms, or it shifts them downfield. Downfield shift. Okay. And so that's why the benzene ring shows up around 6.5 to 8. So 6.5 to 8 ppm for these guys. Oops. Okay, so that was the explanation for the hydrogen within the benzene ring, which is a sp2 hydrogen. However, since it is the electrons are circulating around the ring, it's going to be a little bit different than an alkene. So let's take a look at that. Alright, so basically what we're drawing now is the single bond. We're going to have our hydrogens here. Okay, and then we have basically that p orbital that's sticking up there to create that pi bond, and then we have our, actually let me do that in red for you just to kind of keep with it. Boom, boom, and then our induced magnetic field is going to go in the same direction as it did for the benzene ring. And so what that does is that creates this induced magnetic field that pretty much does the same thing as above, and it amplifies the magnetic field, the applied magnetic field. And so it reinforces it, and it actually results in a de-shielding of the protons on the alkyne. Okay, and that's because of the same thing. So same as above, it feels a greater magnetic field, those hydrogens, so those protons, and so it's de-shielded and results in a downfield shift. Okay, and that's going to be around, just as we stated above, 4.5 to 6 ppm. 4.5 to 6 ppm. Okay, and that's basically the sp2 carbons, or the sp2 CHs, right? And so remember it that way. Okay, so the sp2 are going to be the same. It's just the degree of shielding, or I'm sorry, of de-shielding for the benzene ring versus the alkene. And so for alkynes, however, it's actually a little bit different. So we have, well, what did I draw up here for you guys? I drew a methyl there, and then we had a hydrogen, right? So for this particular structure, it's what we have to do is kind of just rotate our structure 90 degrees, and so we'll have a carbon bond kind of in the vertical position, and then we have our pi electrons looking like this, and then our induced magnetic field created by the circulation of those electrons is going in this direction. Same direction, right? But it's just the location of the proton in question is in a different spot. So before, what we had was the proton kind of sticking to the left and to the right, but now we've got it up here, okay? And so if we kind of, let me draw my arrows to show you the kind of the direction of that induced magnetic field. Now, since this proton and that proton are actually not within that kind of magnetic field that's created, that induced magnetic field, these are actually in a different spot where the flow of that are basically like, I like to think of it as a flow, right, of electrons, right? So the arrows represent almost like the direction of things, the way things are going, and the induced magnetic field actually opposes the external field in the vicinity of that proton. Okay, so this particular proton, the direction of that magnetic field is kind of pointed downward, which is in opposition of the induced magnetic field, right? So you have one arrow going up, and then you have one arrow going down. And so what you end up getting is a shielded proton. Now let me draw this one in like green or something, so that way you can definitely distinguish between the sp3, I'm sorry, the sp2 CHs and the sp CH. So it is a shielded proton now, and what that means is that it is an upfield shift. Okay, and this guy was around 2.5 ppm, right? And so, again, all we have here now is this guy and this guy. These guys are de-shielded. So it's a downfield shift. And then we've got our alkyne. I don't need to do this, but I might as well. It looks like it needs to be there. And this is shielded. And it's an upfield shift. Okay, so that means that it's heading in that direction in terms of ppms, and downfield shift means that it's headed in that direction in terms of ppms. And that's pretty much it when it comes to the shielding and de-shielding explanation of aromatic protons and alkenes and alkynes. So let me know if you have any questions.